This research paper proposes a novel framework called Logic Distillation, (LD), to empower smaller language models, S-LLMs, with the planning and decision-making capabilities of larger language models, L-LLMs. L-LLMs exhibit superior performance in logical reasoning and planning tasks, but their large computational requirements make them impractical for deployment on most devices. S-LLMs, on the other hand, are more deployable but lack the capabilities of L-LLMs. The existing knowledge distillation (KD) approach aims to transfer knowledge from L-LLMs to S-LLMs, but it has limitations. S-LLMs merely mimic the outputs of L-LLMs without comprehending the underlying logic, leading to poor performance in planning and decision-making tasks. The authors argue that KD fails to address the issue of S-LLMs struggling to follow complex instructions and understand the logic of L-LLMs. To address these limitations, the proposed LD framework decomposes the planning and decision-making logic of L-LLMs into multiple stages, each represented by a specific code function. LD then integrates these functions into a function base and fine-tunes S-LLMs to learn and apply the relevant functions. During testing, LD employs a retriever to identify the top K relevant functions based on the current state and instructions, enabling S-LLMs to select and execute functions from this set. The authors demonstrate the effectiveness of LD through experiments in various simulation scenarios, showcasing that S-LLMs can achieve outstanding results in planning and decision-making tasks, comparable to or even surpassing those of L-LLMs. The proposed LD framework has the potential to bridge the gap between L-LLMs and S-LLMs, enabling the latter to accomplish complex tasks with superior performance. The paper presents a novel approach called Logic Distillation, LD, that aims to enhance the capabilities of smaller language models, S-LLMs, by leveraging the superior planning and decision-making abilities of larger language models, L-LLMs. LD consists of three components: L-LLMs, retriever, and S-LLMs. L-LLMs are responsible for decomposing human-provided rules into basic functions to construct a function base, including a user manual that explains the usage of these functions. The retriever is in charge of retrieving the top K functions based on the instructions and states. S-LLMs select the appropriate functions for different stages of the task. The proposed LD framework is summarized in Algorithm 1, which includes generating functions and corresponding user manuals with L-LLMs, building a function base, initializing the planning and decision-making output, retrieving top K functions, selecting the most suitable function for each stage, obtaining intermediate results, and handling emergencies. The paper also discusses the advantages of selection over generation for S-LLMs, as it reduces the entropy of the prediction. Using the Lagrange multiplier method, the optimal probability distribution for each token in the token list can be calculated. The paper concludes that the proposed LD method preserves more general capabilities of LLMs compared to knowledge distillation, KD, which requires S-LLMs to memorize massive ILMS outputs. Here is a combined summary of pages 5 and 6. The paper presents a novel approach to enhance the planning and decision-making capabilities of small language models, S-LLMs, using large language models, L-LLMs, as teachers. The L-LLM decomposes the rules and instantiates the planning and decision-making logic into multiple functions, creating a user manual to assist the S-LLM in learning how to utilize these functions. This approach, called learning from decomposition, LD, enables the S-LLM to comprehend the logic of the L-LLM and execute planning and decision-making processes function by function. The paper also introduces a pursuit game to demonstrate the effectiveness of LD. In this game, two sides are controlled by different LLMs, with one LLM managing 3 blue dots and the other controlling 1 orange dot. The goal is to capture the orange dot within a specified number of moves. The results show that S-LLM struggles to comprehend complex instructions, leading to rule violations, whereas L-LLM demonstrates superior comprehension and ability to follow instructions. The paper compares LD with knowledge distillation, KD, which involves fine-tuning the S-LLM with outputs from the L-LLM. While KD improves the S-LLM's planning and decision-making capabilities, LD outperforms KD in both global and local perspectives. The results show that LD enables the S-LLM to complete the game with an average of 0.96 fewer steps than the L-LLM, indicating its effectiveness in enhancing the S-LLM's planning and decision-making capabilities. The paper also presents visualizations of the planning and decision-making outcomes of different LLMs, demonstrating the superiority of LD over KD. The figures illustrate that LD enables the S-LLM to grasp the planning and decision-making logic of the L-LLM more effectively, resulting in better performance in both local and global perspectives. Overall, the paper introduces a novel approach to enhancing the planning and decision-making capabilities of S-LLMs using L-LLMs as teachers, demonstrating its effectiveness through experiments on the pursuit game. Here is a combined summary of pages 7 and 8 of the research paper. The pursuit game with emergencies is used to assess the capacity of different large language models, LLMs, to handle emergencies. The results show that L-LLM can still grasp the rules through simple textual descriptions and implement effective planning and decision-making, achieving a success rate of 90%. In contrast, S-LLM with knowledge distillation, KD, achieves a success rate of 52%, with failures resulting from rule violations. S-LLM with logic distillation, LD, outperforms L-LLM, with a success rate exceeding 90% and an average number of steps approximately 4 steps fewer than the baselines. The effectiveness of converting logic into functions is further validated by the comprehensive planning and decision-making processes of L-LLM and S-LLM with LD. The paper proposes logic distillation, LD, as a method to improve the performance of S-LLMs, which instantiates the logic of L-LLMs by converting human-provided rules into functions, thereby establishing a function base. Through fine-tuning, S-LLMs will comprehend the usage of each function, enabling them to plan and make decisions function by function. The paper highlights the limitations of larger LLMs, which are difficult to deploy on most devices due to their parameter scale. In contrast, smaller open-source LLMs are easier to deploy but fall short in performance. The proposed LD method addresses this issue by enabling S-LLMs to comprehend the usage of each function, making them more effective in planning and decision-making. The references cited in the paper provide a comprehensive overview of the existing research in the field of LLMs, including knowledge distillation, CodeBERT, and foundation models. Here is a combined summary of pages 9 and 10. Recent advancements in large language models have led to significant improvements in natural language processing tasks, such as text generation, language translation, and question answering. However, these models require massive computational resources, large datasets, and substantial human feedback. Several studies have demonstrated the potential of large language models in various domains, including medicine, finance, and healthcare. For instance, Peng et al. 2023, explored the application of generative language models in medical research and healthcare, while Thirunavakarasu et al. 2023, discussed the prospects of using large language models in medicine. Wu et al. 2023, proposed Bloomberg GPT, a large language model specifically designed for finance. The rise of large language models has also led to the development of more advanced models, such as Llama 2, Tuvron et al. 2023, which offers open foundation and fine-tuned chat models. The survey by Shi et al. 2023 highlights the potential of large language model-based agents, while Xu et al. 2024 provide a comprehensive review of knowledge distillation techniques for large language models. Zhao et al. 2023 present a survey of large language models, covering their architectures, training objectives, and applications. The authors also discuss the challenges and limitations of large language models, including their high computational costs, potential biases, and lack of interpretability. The equation, 1, on page 10 represents the standard formulation of the masked language modeling objective, where the model predicts the masked tokens based on the context. The authors also introduce the concept of knowledge distillation, where a smaller student model is trained to mimic the behavior of a larger teacher model.